This is about where we left off yesterday with finding and classifying critical points of a function of two variables. Our plan was the same plan that we had back in Calc 1 to find and classify critical points. Solve the first derivative set the first derivative equal to 0 and solve it. That would give us a location of the critical points, then classify them by doing something else. We went over a few options yesterday, including using the function, what we know about the function, what we can picture about the function, what we know about the first derivative at intervals of increase and decrease. Both of those are a little tricky here because we don't really have a ready library of functions for dealing with surfaces in R3. We have a few, but this is not in that category, even though it's a nice simple polynomial. So our other option was to use the second derivative and think about concavity. But we're going to have to adapt that as well because we have four second partial derivatives. We have four second partial derivatives. And we got to figure out how to use that, how to use that to classify our critical points. And so that's where we're at today. We want to think about how we use the four second partials . We had two first partials. That leads to four second partials. Let's see what we got. So at 0, 0 and at 1, 1. So at 0, 0, then our second partials are going to be 24, negative 24, negative 24, and 0. So here are the results at 0, 0. I've got the positive second derivative with x twice, negative mixed second partial, and then 0 for the double y derivative. At 1, 1, I've got a positive x derivative. I've got a negative xy derivative, and we have a positive yy derivative. And then I'm going to remember that I didn't bring up the problem to look at the graph. So. I need a little technical difficulty sign for when I forget to bring things up, and then I have to go in and find the problem with like a little sign. It says technical difficulties. We'll be right back. And then some music playing in the background. Okay. Actually, we don't need to look at this. Let's think about what second derivatives tell us. In this first second derivative, we got the fxx. Fxx, and I want to look at the one where we don't have zero, because zero is always suspicious when we are looking at second derivatives. A zero second derivative doesn't tell us stuff. So let's take a look at 1, 1 first and see if we could think about anything what's going on down here. So at 1, 1, our fxx derivative, our second derivative is positive for x. If all we care about is x, we've got positive. So in the single variable case, we would look at this, say the second derivative is positive, and so we have some kind of concave up, and so that says local minimum. And the question is, can we do this in this case? In the fxy, that's a mixed up. That's how x is changing, and then there's also how some y is changing. So this is not really helping us at the moment. But then we look at this fyy and see that one is positive as well. If we just care about the y, we also see some concave up. The reason I'm looking at these two first is it's still a question about whether we could think this way. If we just restrict ourselves to one variable, just the x, we get concave up, we get this local minimum. If we just restrict ourselves to y, we get concave up, and we get this local minimum. So here we are restricting our view to just x and just y. We're thinking of one variable. This is just us thinking, trying to look for how our old way of thinking is going to be applicable in this new environment. If we just restrict ourselves to one variable, then it kind of suggests that at 1, 1, we've got this local minimum. Because in the x direction, I've got something that tells me concave up, and in the y direction, I've got something that suggests concave up. When we look at the graph, since we're trying to figure this out, we need to look at some outside sources. When we look at the graph, at the point 1, 1, if I look at this contour graph, I see that at 1, 1, we've got a -4, and then there's this kind of like almost elliptical ring around it that's at -3, and then at -2. It looks like the contour graph suggests that we are correct in saying there's a local minimum at 1, 1. So the contour, looking at the contours, that suggests that there's a local minimum at 1, 1. That's good. It matches what we thought about when we just considered a single variable. Concave up in the x direction, concave up in the y direction. I don't know what this mixed second partial is. We're leaving that one aside to see if we could just look at x, x, and y, y. And so that suggests that there's some kind of local minimum happening at 1, 1. We look at the contour map, and that kind of supports our conclusion. We're still not sure because we did just like ignore the mixed second partial. It's like, well, these other two fit with what we thought before. That make sense? We just take what we've done before, try to do that again, And then we'll start considering other things that we have to worry about. Which kind of is pretty much all we ever do, like when we're doing science. Take what we've done before and see if it still works. Try something new, come up with an idea, and then try to prove ourselves wrong. Question? That's a good question. Let's take a look at what's going on at 0, 0. So here we use the contour map, and it looks like on the contours, the graph shows that there's a local minimum at -4. Because I got -4 is a low point, and then I've got this ring of -3 all around it. Since this is a continuous function, there's not going to be some weirdness going on. Otherwise, the equation would have shown us another critical point somewhere in this little ring here. There isn't. So we've got this ring of -3 all around this single point where it's -4. Let's look at what's going on at 0, 0. Now that we've got this, now that we've got the contour map just like right in front of us. If we look at what's going on at 0, 0, I've got this contour that runs right through the origin. And we can see that. We're not surprised that this happened. Because when we look at the function, there's no constant term. So at 0, 0, the value of the function is going to be 0. But moreover, we've got this line of 0 running right through it. So this point, this at 0, 0, it doesn't look like we're getting a low point. It's on a contour. There's a whole line of 0 running right through. This 0, it looks like it's sitting in some kind of valley. Because if we go up here, we're at 1. And if we go up here, let's see if this one, it looks like this middle one is 2. So it looks like there's a 1 here. So at least going in this direction, it looks like we've got some kind of valley. But then going in the y direction, if we go up and down in the y direction, we could see this other line of 0 running through it. So everybody see that at that 0 point. At that 0 point, I've got this ridge running through it where it's a low point. Here's a 1 down to 0 up to 1. So standing here and looking in the direction of, say, 135 degrees and 315 degrees, we see it going up. But if we look at 45 and -45, we see it falling down. The contour map is suggesting that we're in a valley in one direction, but on a hill in another direction. The reason that we're doing this, once again, is if we look at our second derivatives, at 0, 0, we had a second derivative of 0, which means that this second derivative test stuff ain't gonna work. The second derivative test doesn't work when we get a 0. It doesn't. The second derivative test is not telling us stuff. It might be a max or min. It might be an inflection point. We can't tell. That's why we had to look at the graph. So in this case, the contour is suggesting a saddle point at 0, 0. It looks like in one direction, it's a minimum, but in the other direction, it's a maximum. A minimum in one direction, maximum in the other. That's what we mean when we have a saddle point. It's a minimum in one direction, maximum in the other. So far, this is still obliquely lining up with our thinking from before. Second derivative positive means concave up, means local minimum. Second derivative 0, not telling us anything. Doesn't perfectly line up because there's other stuff going on. There's still this mixed second partial. How does that show up? We've still just been kind of ignoring that in this process. So things aren't lining up perfectly. We got multiplication at an angle. It looks like we have the dot product of our old thinking and the new thinking. Those of you following along later, the example that we're looking at is the contour. The contour will be shown in section 15.1, example number 4. So it looks like we can see some elements of our previous thinking, our single variable thinking, still hold here in this multivariable case. But we do have to deal with these mixed partials. How do these mixed partials get involved? So there is some similarity to our single variable second derivative test, but there is some stuff we ignored, like in particular those mixed second partials. How are they going to enter into things? Any questions on the parallels that we're trying to draw? Remember what we try to do. Always start with what we already know and see if that applies. 3 great tricks of math. Add 0, multiply by 1, do problem you already know. Get distracted by the fact that the bases of these chairs are like asymmetrical. They have the 4 legs, but like 2 of them are higher than the other one. And now I'm going to be stuck wondering, for like physics reasons or for like design reasons. I know I probably shouldn't have said anything because now some of you are going to be distracted, but I mean, usually when I'm suffering, I like to spread that around. I'm not really suffering, I'm just distracted. Is it like a style thing, or because what that suggests to me is that the chair definitely has a front, right? There's definitely a front to the chair. Not just the chair, the part that you sit in, but there's a front to the base of the chair, but I also noticed that the chair part has 360 degrees of movement. So the chair definitely has a front and the base definitely has a front, but they don't have to agree for you to operate the chair. You could sit in the chair with the front of the chair facing the back of the base, or even the front of the chair at like 112 degrees off of the front of the base. It's just, why do people that make chairs do this to me? I know it's not me in particular. Some of you as engineers, you need to figure out why the two legs on one part of the chair are higher than the other ones, so that you can tell me which part of the base is the front of the base. That's what I need to know. All right, interlude over. Stop being distracted. All right, so let's look at the second derivative test for the function. Let's look at the second derivative test for a function of two variables. So we need to find a way to combine the four second partials. We're going to make a one function of two variables that combines the four second partials. We're going to make one function that combines all four of the second partial derivatives. So this is the function that we're going to use. We're going to be able to plug our critical points into this function, which is a combination of our second partial derivatives. Then we're going to look at the sign of this function and use that to classify the equation. Then we're going to think about how this is constructed, because it looks a little bit weird. I've got fxx times fyy minus fxy squared. I threw in all the xy's because we want to remind ourselves that we're going to be plugging points into this, but this function d is fxx times fyy minus fxy squared. We can get away with fxy getting squared because we're going to be doing this where functions are continuous, and then the mixed second partials will be equal. So I don't have to say fxy times fyx. I can just say fxy squared. Here's how the thinking goes. If this function d is positive and fxx is positive, then we see a local minimum. This matches what we thought before. Second derivative positive, local minimum. I'm looking at d, which combines all four of our mixed partials, all four of our second partials, and then we just look at fxx. If fxx is positive, then we say local minimum. In the example that we had before, so from our previous example, I'd have fxx, which is a constant 24, fyy, which is a constant, which was 48 times y, which is 1, so minus fxy, which was a negative 24 squared. Yes. No, that's parentheses around the f. So I got 24 times 48 minus 24 times 24. So that's going to be, don't care, it's going to be positive. And fxx was the 24. Which is also positive. Since these are both positive, we conclude that there is a local minimum. That's what we suspected originally. That's what we confirmed by looking at the contour. So there are the conditions where we can conclude local minimum. Here are the conditions where we can conclude local maximum. We say local maximum if this quantity d is positive and fxx is negative. The fxx, that second derivative being negative, says local max. That's normal. But this combined second derivative function, this d function, has to be positive to conclude local maximum. Our example didn't have a local maximum. So it looks like the second derivative part with just the one variable seems to match up, but to conclude local maximum or local minimum, the d thing has to be positive. This d function has to be positive. There's a third thing that can happen. If this d function comes out negative, then we have a saddle point. It's a maximum in one direction and a minimum in the other. If d shows up as negative, then we just stop. We don't even bother looking at the individual derivatives. We just got saddle points. In our example from before, d of 0, 0 was 24 times 48 times 0 minus a negative 24 squared. Since this is all 0, we're subtracting whatever negative 24 squared is. So this is going to be negative. And, oh, that's it. We don't need to worry about anything else. This d function made up of the 4 second partials is negative. So therefore, we can conclude saddle points at 0, 0. Here are 3 things that can happen. Have we covered all of our bases? You can tell by the way I'm asking the question, the answer is no. What's missing? What's the last thing I have to cover? D is positive, f of x is positive, d is positive, f of x is negative, d is negative. What's left? Nope, we've covered fyy. If d is equal to 0, if this d function is equal to 0, then the second derivative test provides no conclusion. Just like before, when our second derivative was 0 at a point, we did not get to use that to determine if we have a local maximum or a local minimum. We don't know what's going on. The second derivative test, not saying anything. So that's mirrored here. So in a way, this d function is kind of mimicking that part, at least that the inconclusive part of the second derivative test, our original second derivative test. But other than that, it's behaving kind of strangely. If this combined function, this d function is negative, then we immediately say saddle point. If d is positive, then we have to look at fxx and see if that's positive or negative, and that tells us whether it's a local maximum or a local minimum. The question in the chat was very significant. Why in none of this do we ever worry about what fyy is doing? Right? So question from the chat, thank you very much. That is a perfect question. What about fyy? Why did we not consider it here? That seemed to be pretty important when we were discussing this before. I only said local minimum after I saw fxx was positive and fyy was positive. Why can I just so blatantly ignore it now? What about fyy? Why do we not, the second derivative test, why does it not seem to worry about what's going on with fyy? So specifically, why do we not care about fyy in this second derivative test? This is a relic from the past. If our second derivative test is equal to 0, then we don't get anything from the second derivative test. Then it's a matter of reading signs. It looks like we're reading the signs of fxx, but only if this d function is positive. If the d function is negative, I don't worry about anything else. I can just immediately conclude that there's a saddle point going on. How's everybody okay? Yes. If d equals 0, then the second derivative test provides no conclusion. Classic second derivative test maneuver. The next way we make the decision is not whether we look at whether d is positive or negative in the traditional sense. If d is positive, then we look at fxx, and the sign of fxx determines whether we have a local maximum or a local minimum. But only we look at fxx only if d is positive. If d is negative, we immediately say saddle point and then move on with our lives. So the 0 parts, not providing a conclusion, classic second derivative test maneuver. This part where we look at fxx, whether it's positive or negative, and determine local minimum or local maximum, that also seems like the old style. We look at the second derivative, if it's positive, local minimum. If it's negative, local maximum. But we only do that if this d function, if the combined function is positive. When the combined function is negative, I don't worry about the individual second partials. We just say saddle points. And so the question that I have now is, why does fyy not show up except in the combined function? Why do we make this decision based on fxx and not fyy? You can probably tell by what time it is what question I will not be answering today, because I want you to think about it. Don't worry, it's really kind of an algebra question. Look at the way we built this function d of xy. And then discover why we don't care about fyy looks like. Or maybe if we want to care about what fyy looks like, what could we get rid of? All right, so think about that. What about fyy? Figure out why we did not need to bring it up in this second derivative test. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.